This new lesson in Unit 2 is going to introduce us to inequalities, which is what this unit is all about. And we're going to focus on writing and graphing inequalities, a lot of which you probably have seen before. So this will be just a good refresher more than anything. So an inequality, let's write that down. An inequality is simply a mathematical sentence that compares two expressions. And more specifically, it compares expressions that are not strictly equal to each other. They're either less than, greater than, or less than, or equal to, or greater than, or equal to. And so when we're writing an inequality from a word problem, we want to be on the lookout for what words are the key words that are going to remind us that we should be writing an inequality. Some of them are really obvious, like the actual name of the figure. So this is our greater than symbol. So it might be just as simple as the problem says, some quantity is greater than this other quantity. So sometimes it's just that simple, greater than. Or sometimes we say more than. So something is more than something else. If it's less than, similarly, a lot of it is really a lot of times the wording is pretty straightforward. They might say some quantity is less than another quantity, or fewer, right? Sometimes we say this much is fewer than something else. The less than or equal to or the greater than or equal to do get a little bit more interesting. It could still be pretty straightforward. I mean, it could still, for this symbol, for example, it might just say, some quantity is less than or equal to something else. But it does get a little more interesting. This is actually a more common vocabulary, and it can be a little bit deceiving. A lot of times we say is at most. Or is no more than. And the reason why you want to be extra careful with these is because we see the word most or more, and our instinct, if we're not paying close attention, might be, oh, most and more, that's big, we should go greater than. But this actually kind of means the opposite. If I say at most, say that, say I'm trying to be better about my soda intake, and I say, you know what, I'm going to make it my goal that I drink at most 2 sodas a week. That doesn't mean I want to drink equal to or greater than. I actually want to keep it less than or equal to, but I don't want to go anything past that. I want to go bigger than that. That is a most that I want. So I might say my goal is to drink at most 2 sodas a day. That would be a less than or equal to. The number of sodas that I want to drink is less than or equal to 2. Or no more than. Like I want to make sure I drink no more than 2 sodas a week. Okay, that would indicate that I want to keep it less than or equal to. So even though you see these words right here, our symbol is actually a less than or equal to. And then same thing with the greater than. It might be pretty straightforward, and it might say something very obvious, like is greater than or equal to. But it might be kind of like these guys. Sometimes we say is at least, or maybe is no less than. And again, we see that word least or less, and we might be inclined to use this symbol, but this really means a greater than or equal to. For example, if I say, you know what, I really want to make sure that my grade in this class is at least an 85. That doesn't mean you want to get less than an 85. It means that you want to get either greater than or equal to an 85, but you don't want to fall below that. Or if I say I want to make sure that my grade in this class is no less than an 85, we'd be implying, again, that we want our grade to be greater than or equal to. So even though you see these words, we really mean we want to stay greater than or equal to that. So even giving yourself a quick example like that when you have a question typically helps you decipher which one. So just be on the lookout for those. Those can be a little bit misleading if you're not careful. All right, so we know the vocabulary and we know what the symbols mean. Let's talk about graphing, because this is a big piece. A lot of the steps that we take when we start to solve inequalities will be very similar to equations. One of the big differences is, though, that unlike equations, we typically graph our solutions for an inequality, showing on a number line what all, the range of all the values that make something true. So, for example, if I have x is less than 2, we know that that means symbolically or algebraically, this right here, x is less than 2. This is in words, this is algebraically. And then on a graph, what I would like to do is then show, because the idea here is that there's more than one answer here. Anything less than 2 works. So -5 makes this true. -1 makes this true. 0 makes this true, and so does number 1, right? So even like 1.9, to be honest, right? It could be a decimal. It's still less than 2. So there's an entire range of numbers. That's why we typically graph it, because there's more than one answer that makes it true. And so we show that on a number line. Now let's review how we graph these inequalities. So if I want to represent on this number line all the x's that are less than 2, then what I want to do is find that 2. That's what I call the boundary number. And we'll put a circle. I'm going to do it above so you guys can see it a little better. Some people put above, some people do it right there on the line. But I'm going to make that circle. Now, if I want everything strictly less than 2, but not including, notice I don't have that little bar. It doesn't include 2, it's just less than 2. Then I'm going to leave that circle empty or open like it looks right now. And then I'm going to draw an arrow, or you can sometimes, highlight the number line in the direction that contains the solution. So all the numbers that are less than 2. That would be the numbers in this case to the left, where these numbers are all smaller than 2. If I had wanted greater, I'd go this way, right? But we want smaller. So less than will always be to the left on a number line. And so it would be coming this way like that. And then you could, like I said, either do it, highlight it, or make your number line, just kind of darken it in that way. So that's what that graph would look like. If I want all the x's that are greater than 2, algebraically that would look like this. I would still have a boundary number at 2. It does not include 2. This is still just greater than, but not including, so I leave it empty or open. But this time I would want to sort of emphasize or highlight all the numbers that are larger than 2, which would be to the right. So that solution would look like that. And then you kind of get the idea, except here we want all the x's that are less than or equal. So that would be this symbol. And I would still mark my 2. I would still mark my boundary, but this time 2 is included in the solutions. It could be anything less than or equal. So 2 is okay. 2 is invited to the party. So we fill that circle in. We shade it in nice and clearly. So you see the obvious difference between when it is not included and when it is included. And again, we'd be less than, so it'd be basically anything that equals 2 or is less than 2. Okay. And then you can imagine what this one looks like. Greater than or equal to looks like that symbol. 2 is still our boundary in this example. It is now included, so we're going to fill that in like that. And then everything greater would be to the right. Okay, so that would be just the examples on for how we would graph the solutions after we've come up with our final inequality solution. Okay, all right, let's flip that over. Do a little bit of translating practice here before we really move in to some solving or some, we're not solving today, but to some graphing. So it says 12 is at least 5 times a number n. Okay, so let's think about what that would look like. Okay, so we start with 12. We've got 12 is at least, so again, be careful with this, right? We talked about this just a moment ago. When we see at least, that actually means greater than or equal to. That means 12 is at least, it's got to be greater than or equal to 5 times a number n, so 5 times some number n. So that would look like that. Okay, and let's try this one. This one says 1/3 of a number. So that part right there would be 1/3 would be this fraction. When we do 1/3 or a fraction of a number, that means we're multiplying it by that number. So that's 1/3 of a number. Is at most, again, be careful with that word. That means we actually need it to be less than or equal to that 15. Okay, that means if it's at most 15, that means we want it to stay under or equal, but not go past. So there it is. Okay. Let's try one more, and then you can try number 4 on your own. This one says 7 is less than or equal to, so this one's more straightforward. So 7 is less than or equal to the difference of a number q and 6. So it's less than or equal to the difference, so that's a subtraction of q and 6. So that means these two quantities subtracted. Okay. Try number 4. See if you can write that expression there, and then you can check it. And if you got, it says the sum of a u and a number, so if you got u plus 14 is more than 6, then that's exactly what you should get. That looks good. Okay, so let's talk a little bit about the solutions. A solution of an inequality is a value that makes the inequality true. Now, that was the solution to an equation as well, but the big difference is that an inequality can have more than one solution, right? It could be a whole range of values. And so the set of all solutions in an inequality is called the solution set, since there's more than one. Solution set. Keep that in mind. Make sure you're writing it down, okay? So this is what we mean by that. We're going to do a little bit of solving here, or at least plugging in. So it says, tell whether the value is a solution to an inequality. So I've got this inequality here. It might look a little familiar. It looks a lot like the equations, but this symbol right here changes the game a little bit. And we want to know if d equals 19 is a solution. So they've already given me a value. We're just testing it. We're just testing to see whether this makes this inequality true. So what we'll do is we'll insert that 19 for d and say, okay, if we plug in a 19 here, does it make this inequality true? That's the question, right? Well, 19 minus 7 is exactly 12, and my symbol is a less than, a strictly less than symbol. So the question here is 12 actually less than 12, right? Not less than or equal to, but less than, right? The answer is no, this does not work. Okay, so then we can say this is not a solution. Okay. You try number 6, see how that goes. Check to see if when n is equal to 1, that inequality is true. Okay, so check your work here. If you got 9 is greater than or equal to 9, you did the math correct, and then we can conclude, is 9 either greater than or equal to 9? Remember, it's an or, not both. It's one or the other. So does it make either of those things true? The answer is yes, it is or equal to, right? 9 happens to be equal to 9, so that does work. So the answer here is yes, that one does work. So n equals 1 is a solution. Okay. And we're just going to recap just a little bit here about what we did earlier on the other side as far as the graphing. Basically, we graph to show the entire set of numbers. So the graph of an inequality will show you the solution set of that inequality on a number line. Okay, and so when we have a boundary number that is not part of your solution, we leave the circle empty. So that's an open circle. And then a closed circle, like that, is used when the boundary number is a solution. Okay. And then we use the arrow to then point in the direction of the rest of the solution. So an arrow to the left or to the right shows that the graph continues infinitely in that direction, right? That all of the numbers in that direction make that inequality true. Okay. All right, so we're going to practice just a little bit of graphing here, and we will wrap it up with that. So let's try a few of these. Again, look, these are already solved. X is already isolated. It's just a matter of taking that inequality and practicing how we would represent the same solution but on a number line. So if we take a look at number 7, we've got all the x's that are greater than or equal to 3. So the first thing we'll do is we'll look for that boundary number 3, put a circle on it. If it equals, if we see this bar underneath and we know x is allowed to be equal to 3, we will indicate that by filling in the circle. Okay. And then last but not least, if it's all the x's that are greater than or equal, so we already took care of the equal. As far as the greater than, values that are greater than your boundary should always be on the right side. Like, for example, 4 is greater than 3, 5 is greater than 3. If we plugged in anything on this side, it would make that inequality true. So then we would make an arrow that points in that direction. Okay, try number 8 on your own. Okay, so here, if you put a circle on 4 as your boundary, and you filled it in because it's or equal to, that looks great. And since this was less than or equal to, then the rest of the solution set is all of these numbers that are to the left, everything that is smaller than 4. Okay, and we put the arrow that way. We know that even if we don't keep going forever and ever, we know that it's basically everything in that direction. Okay, let's try number 9. If we have on number 9 just the greater than. Okay, so we would put our boundary here at -1. This time it doesn't equal, so we're going to leave it empty. And then we just make sure the arrow points in the right direction. So if it's all the x's that are greater than -1, again, the numbers that are greater than should always be to the right. Okay, so what if we're going in the opposite direction? We'll finish off with that. What if we have graphs? What would that inequality look like if we wanted to write it algebraically? So we're sort of working the opposite of 7 through 10 here. I have a graph, and it indicates that in this particular number line, the solution set is all of the numbers that seem to be greater than 1. So my boundary, I can notice here my boundary number is 1. Is it included? No, it isn't, because it's an empty or open circle. And I can see here that it is the right side that is darkened or shaded in where the numbers are greater than. So this is a strict greater than symbol. So I could say here that all of these values that seem to be the solution are x's that are greater than 1. Like that. Okay. Let's try one more here. Let's try number 14. So number 14, first of all, it's identified. If you want to put your variable, go ahead. Our boundary number is 3. Okay, and then as far as our symbol, does it include 3? It does. Notice the difference between these that are open, and this one is definitely filled in by comparison. But this time we're shading to the left, which is all of these numbers that are less than 3. It's saying that these are the solution set, so I need to make sure I use the correct inequality, all the x's that are less than or equal to that 3, like that. Okay. All right, let's finish off with one of these, actually. And then we'll leave the other one, and the back page we'll actually be doing as an activity in class. So it says write and solve an inequality that represents the missing dimensions here. The area is less than 42 square meters. So I'm going to remind you that for a triangle, the formula, the original formula for the area is always 1/2 the product of the base and height. That's always the original formula for a triangle when we're doing area. So let's fill in what we know. Okay, we know that the 1/2 is still there. Our base is x. And our height is 6. And what they're saying here is that this area, this right here represents our area. Okay, this area is less than 42 square meters. So whatever this result is, it's less than 42 square meters. Okay, so instead of it saying it's equal to 42, we're saying it's less than 42. So we set it up like this, and now we really solve this with the exact same techniques and steps that we did with equations. We'll simplify this side, so 1/2 of 6, we can definitely do that. 1/2 times 6 is 3, so this just really simplifies to 3x. So it looks like that. And then to solve for x, we just divide by 3 on both sides, here and here. And I get that x is less than this quotient, 42 divided by 3. That happens to be 14. And this is still in meters. So what we're saying here is that in order for this triangle to maintain an area less than 42 square meters, that means that this base has to be less than 14 meters. That's the only way that that would be true. So the base would have to be less than 14 meters so that the area ends up being less than 42 square meters. All right, that's our lesson on inequalities.